Hello, so in this video we're going to look at how to solve a problem that looks like this, a first order ODE problem that looks like this. Now this is something that we haven't looked at before, because if you think, okay, we've sort of dealt with how to solve first order ODEs. We solve them primarily three different ways, or there's, depending on the type of form that it's in. So either we can use what's known as separation of variables. Okay, separation of variables. So say if we have something that looks like this, so dy by dx equals, 4x, 4xy, let's say. Okay, then you can solve that by separation of variables by getting everything involving y on one side. So you get 1y, dy by dx equals 4x, then multiply through by the dx. So we get everything involving y on one side and everything involving x on the other side. Then we just integrate like that. Okay, so that's how to solve something that looks like that. If we have something which looks like the form dy by dx equals, plus p of x, say p of x y equals q of x, say. Okay, so this is a case with constant coefficients. Okay, this case now is with variable coefficients. Well, then we solve it by using something called an integrating factor. An integrating factor is just e to the integral of this coefficient here. Okay, so that's how we can solve this type of problem. And also, if we have something, if we can get something in the form of using exacts and non-exacts as, separation, separal equations. So in other words, we get a function m of xy plus another function times dy by dx. Times dy by dx. Okay, set it equal to 0. Then you can solve that by using non-exact and exact and non-exact equations. Okay, exact and non-exact equations. And the process is pretty much the same, right? Okay, there exists some function which then, when differentiated with respect to x, is equal to m, and when differentiated with respect to y is equal to n, and then you kind of solve it from there. Okay, by sort of solving separate equations. But look at this. Look at this now. This is what we've got here, right? Well, this isn't in any one of these forms, because look, we can't separate it. Okay, we can't separate it up because we've got an x plus y inside a cos function. So we can't separate it very easily. So we can't use this, we can't use this, and it's not looking linear because it's not looking like this. Okay, because there's no y being multiplied by it. Okay, because look here, if it looked like this second one, we needed a variable coefficient which depended on x only. I mean, if it was something that looked like this, dy by dx equals cos x times y, then that's absolutely fine. We can use this second one, but because the x and the y are inside what's known as the argument, which is the thing inside the cos, then we can't use that either. So we can't use any one of these techniques as it stands to solve this equation. So we've got to be a little bit clever, right? So obviously the thing which is the most awkward thing is this argument in here, because it's dependent on both x and y. So when you're faced with something like this, I don't know whether your mathematical intuition is telling you anything at this moment, but we've got something in here that's dependent on x and y. That's what's making it awkward. Now, when we've got something that looks awkward in an equation, what we normally do is just make a substitution to make things easier. So let's say, for example, so I'll write it out again. So let's say that this hard thing in the middle, this difficult thing in the middle, the x plus y, is just equal to z. Okay, x plus y. And remember that y is a function of x. Okay, y is our function that we're looking at. X is our variable. So therefore, that means that z must be a function of x as well. Because look, z has got x in, and it's got a function which involves x in. So therefore, it will all be dependent on x. Okay, so z is a function of x. Okay, so we can just make the substitution now. Dy by dx is equal to cos of z. Yeah, cos of z. So I've just made a substitution for x plus y. Right, so z equals x plus y. Right. But we also need to make a substitution for this y here. Well, what's this? So y is equal to, from this z, we can just say that y is equal to z minus x. Right? So therefore, if we just make the substitution, so we end up with, so I'll just ignore that bit for the minute. So we just end up with dy, which is just z minus x, okay, is equal to cos z. Cos z, okay. So what's the derivative? So this is just the same as the derivative of z with respect to x. Just multiply this dx through, okay, minus the derivative of x with respect to x is equal to cos z, right? Well, derivative of z with respect to x is fine. This is just 1. This is just 1, right? Because the derivative of x with respect to x is just 1. I mean, again, if you treat this as a fraction, this just cancels down to 1. But what this is also saying is, what's the derivative of x with respect to x? Well, it's obviously just going to be 1. Okay, so this is just 1 now. This is just 1. Okay, so therefore that implies that dz by dx is equal to, just do 1 plus. Take the 1 over the other side, cos z. Okay, so therefore what we've done is we've converted this now into something that we can deal with using our traditional forms. Okay, so we've kind of got it into a form that we can deal with now. Okay, and the way which I'm going to deal with it is going to be by separation of variables. I think that looks kind of a nice way which you can deal with it. Which other way can we deal with it? We can't. Just separation of variables would be the only way. So in other words, we're looking at this case up here. Looking at this case up here. Okay, because look, if we divide through by this to get everything involving z on one side, so we end up with 1 over 1 plus cos z dy by dx, sorry, dz by dx, is equal to, well, this is just 1 now on this left-hand side, because I've just divided through by 1 plus cos z. Okay, so then if I just multiply through by dx, to get everything involving x on the other side, then just take the integral of both sides. Okay, this is now an integral that I can work out. Well, this integral on the right is easy enough. Okay, this is just x, and I'm going to include my constant of integration on this right-hand side. But this is a little bit more tricky to kind of try and work out, because it involves, you need to basically know your angles, your angle identities, or your trig identities. Okay, well, note that double angles. Okay, so we end up with cos 2a, for example, is equal to cos squared a minus sine squared a. Okay, now look, we want basically make a substitution for cos z. We want to make a substitution for cos z. There are other ways of doing this, by the way. There are other ways of doing this. Well, we also know that 1 plus cos squared plus sine squared equals 1. So therefore that implies that sine squared is equal to 1 minus cos squared, right? So we can just make a substitution for this sine squared now by just saying that cos 2a is equal to it'd be cos squared a minus 1 minus cos squared a. Okay, so when we expand this out, we'll end up with minus minus, that becomes a plus, so it'll end up with cos squared plus cos squared, so this will become 2 cos squared, okay, minus 1. So 2 cos squared minus 1. Now we just want to make a substitution for cos z, so therefore if we let z equal 2a, then that implies that a is equal to z over 2, right? So therefore I end up with cos z is equal to this thing. It's going to be 2 cos squared a, which is z over 2, minus 1. Okay, so now if I make just a substitution in this left-hand side, all I'm just going to do now is just consider this integral. So we just end up with the integral of 1 over 1 plus cos z, okay, dz. Well, I've just said that cos z is equal to this thing, so it's plus 2 cos squared z over 2, right, minus 1. Okay, well the 1 and the minus 1 will just cancel out, so I'm just left with 2 cos squared z over 2. 2 cos squared z over 2. Cool, okay. And that's equal to x plus c. Yeah, because this is just from using that thing there now. Okay, so this is just all equal to cos... it's just equal to x plus c. Okay. Now notice that the derivative, you know, you really need to know your kind of trig identities for this. There are other ways probably of working it out. But, you know, trig identities is just one way of working it out. So I'm just taking you through that method. If there's another way which you kind of find easier, absolutely go for it. But I'm just going to go with this because I kind of know my trig identities. What's the derivative? What's the derivative of tan? What's the derivative of tan? The derivative of tan, you can work it out just by using the, well, I use it using the product rules. It's basically the derivative dA of tan is sine over cos. And then I can just raise this cos to the minus 1, yeah, times cos A to the minus 1, okay, and then you kind of work it out from there using the product rule. So it's going to be derivative of this thing, which is cos, times this thing left alone, times cos A to the minus 1, yep, plus the derivative of this second thing, which is going to be minus cos A to the minus 2, cos A to the minus 2, times the derivative of what's inside the bracket, so it's just a chain rule, right? We just find the derivative of that thing at the moment. So that's going to be minus sine, so maybe that becomes plus, minus sine A times this thing left alone, so I'm just going to do sine squared A. Okay, so this then becomes cos A over cos A. Yep. Plus, what have we got? We've got sine squared A over cos squared A. Cos squared A. Okay, well, if I now look at this first fraction, right, this first fraction, I want to make the denominators the same, effectively. So if I just multiply through by cos squared of this first fraction, multiply this first fraction by, you know, cos A over cos A, okay, times, if I just multiply top and bottom by cos A, yeah, this then becomes cos squared A over cos squared A, yep. Just do that, okay, and then I could just write this over the same denominator, okay, so just over cos squared A, yep, and this cos squared plus sine squared is just 1, yeah, so it becomes 1 over cos squared A. So the derivative of tan is 1 over cos squared A. Well, that's effectively what I've got here. Except obviously it's a z over 2. But if I just say that, then well, what's the derivative of the derivative with respect to z of tan, I don't know, tan, what would it be? Tan z over 2, is that right? 1 minute. Yeah, what's the derivative of tan z over 2? So in other words, I'm just replacing a with z over 2. What's the derivative of that thing? Well, I know that it's going to be 1 over cos squared z over 2. Okay, but it's the derivative rule. So I know that the derivative of tan is going to be cos squared of that angle multiplied by the derivative of whatever's inside this chain rule. So whatever's inside the brackets. Well, the derivative of z over 2 is a half, so I'm going to have to multiply by half out the front here. Multiply by half out the front here. So therefore it becomes 1 over 2 cos squared z over 2. Okay. So therefore I can basically say that the derivative of tan z over 2 is 1 over 2 cos squared z over 2. Well, that's exactly what I've got here. So therefore the integral of that must be tan of z over 2. Okay, and that's still equal to my right hand side. Okay, so now I've kind of solved it, but I just want it written explicitly as z. So z over 2 is just going to be equal to arc tan of x plus c, right, of x plus c. So therefore z must be equal to 2 arctan of x plus c. Okay, so that's kind of a nice way to solve it. So, you know, I've solved, where are we? What have I solved? I've solved this problem. Okay, I've solved this problem in terms of z. But what was z, remember? What was z? Well, z was x plus y. So now if I just replace z with x plus y, then I'll get my final answer. So that implies that x plus y is equal to 2 arc tan of x plus c. Okay, so therefore that implies that y, because I want what y equals, y is equal to 2 arc tan of x plus c minus x. Okay, and there is my final answer. So in other words, that's just by substitution. I've just taken you through substitution. I think you could have probably done the the substitution is basically the difficult part. You know, you just basically make a substitution for, what do we start off with? Start off with here. You know, the trouble was because the x and the y were contained within the same function, the cos function. It's going to be difficult to separate. I mean, you could have tried separating this using your angle formula. So what is the angle formula? Cos of a plus b is equal to cos a cos b minus sine a. sine b. So you could have tried approaching it in that way, but because, you know, that looks kind of more difficult to me, to be honest with you, you know, I just solved it using this way, just by making a substitution for z, right? And you end up with this answer here. So that's a good way of doing it. Basically, the hardest thing was the substitution. I just wanted to show you an example using substitution.